So let's start it over again. So again, I want to thank everybody for being here. It's truly an honor to make this a talk with you all and share some of the current research that I'm doing here at the University of Florida. Just to mention where I stopped, I became knowledgeable of real-time monitoring through quasi-static models, state estimator models in the late 90s, where the domain of application at the time was wide area protection systems. And more recently, I've been working towards cyber-physical security of the grid. And I will try to briefly share with you all the current challenges that we're trying to address and the current vision that we have to address them. So overall, I've been working on currently on several topics. I've been fairly, let's say, successful in receiving some funding towards some of the visions for research that I and my group have here at University of Florida. And today we're going to talk about cyber physical security of the grid, and real-time monitoring is the specific domain of application. And of course, when we talk about CPS security, it's pretty much a broad, general topic. So we have people that are coming from different backgrounds and doing research in the same theme. And I will give, of course, one perspective, but that is, of course, not limited. You should consider that one might have several research challenges that one can address. And I'm specifically talking about one application that runs in the grid every so many seconds, which is real-time monitoring of the grid. And the vision that we're being imposed to implement is how does one go about using models. So using models, and they can be quasi-static models or they can be dynamic models. So using models, but also using data, right? And using data in, if you will, a reinforcement learning approach. So when one can help the other. So when you can model so much, and how can you use data towards improving the process. And this specific application is regarding CPS security of the grid.
Excuse me for a minute. Can I
Yeah.
ask Robin to record this since we're on a different channel?
Yes, absolutely. Yes.
It's recording, George.
Okay, good. Thank you.
So one nomenclature that I would like to share with you all here is this definition of smart grid. And depending on who you talk with, you have one vision, but overall, you have some common aspects, and it's really a vision of the grid for the future. And in this vision, one talks about the increased use of IT and OT technologies in mainly on the distribution network. Several technologies are being implemented and built on the distribution networks. And of course, you talk about, remote control and automation. So it's truly a path. So it's not a vision that the grid was not smart at all. It's towards a smarter grid, I guess, is the way that I like to look at it. Now, of course, when you increase the use of IT and OT and increase the use of remote controls and automation, you also increase the risks associated with security, and you increase the risks of having problems as different types of cyber physical attacks that can, of course, cause problems. And the talk today will concentrate on these risks. And the vision first is, how do you model these risks? So what are the risks that you're talking? And we, of course, want to relate that with the physics. And after going about modeling these risks, or these attack types, if you will, how do you go about detecting them, identifying them, and then correcting these potential attacks? So of course, when we talk about smart grids, we come with the vision of a vertical integrated system where you have generation on one side, and then you have transmission and distribution on the other side. And suddenly you start having all these technologies spread out through the grid, where generation is actually where once was only the distribution. You have biflow uh, uh, powers in the distribution network, and you have IT and OT, and you have demand response. You have all these technologies installed. And what I wanted to show with this slide is that, of course, when you have that, you have also the risks involved of those. And there's several applications. So just to mention a few, you have potential attacks to real-time monitoring as what we call non-technical power losses. So that's energy theft. Or you have, attacks that are in the protection or control systems. So you have several different types of attacks that actually don't need to be only on what we call the smart grid layer, which is what one has been used to use towards real-time monitoring or state estimation, which are voltage measurements, power flow measurements, power injection measurements, but they can be also in other layers of the system as we know it, as the communication layer, meaning denial of service attacks and spoofing attacks. So they can happen on these layers that so far are seen kind of isolated, but really are interdependent. And it's just that we don't model these dependencies through physics or through data, and we just consider them kind of isolated, but they truly are integrated. And of course, when we start using them, even if we're not modeling these relationships, we have an augmented risk, if you will. So the challenges are in place, and the answer then is how to attend, if you will, society's expectancy regarding efficiency in a secure way. And what we have been doing here at the University of Florida is try to present and propose and implement algorithms that overall increase the efficiency of the process and the security. So you want to, at the same time, increase dependency and security, which sometimes are contradictory, right? So one is, of course, proposed when you want to act, when you're supposed to, and the other one, security, is supposed to, your design or your end goal is to not to act when you're not supposed to act. So these contradictory goals where one can try to propose metrics is what we try to increase simultaneously through new algorithms, if you will. So regarding the specific topic of today, we are talking about real-time monitoring, and that is currently done through state estimators, and every utility or ISO or DSO or will be running these, and they usually ran every 60 or 90 seconds, while measurement scans are done every 4 or 6 seconds. And those are what we call the dynamic data. So these are measurements and system states, as for example, states of switches or circuit breakers. And measurements are usually RMS measurements, as real power flows, power injected, reactive power flows, and voltage measurements. We also have what we call the static data. So that's where system parameters are in place, and that's usually at the operating center at some specific server that has all this data. While the dynamic data is monitored, you have actually a pre-filtering stage. Static data is not. And both of them, if you will, are used towards topology processing. So that's where you will, from the data, create, if you will, a topology, the one-line diagram or the bus line diagram of the system. And through that, you're going to analyze what we call observability of the system, which means that with the data at hand and with the connections in place, are you able to estimate the system state? And the state variables can be defined as several, but overall, the great majority of applications nowadays use voltage, magnitudes, and angles as state variables. And what you want at the end of the day is to run the state estimation. And we're going to see that it's basically a constraint optimization problem. And in that problem, you will try to estimate the best, if you will, states that acquaint to your measurements and your topology. And when you do that, you have what we call the post-processing stage, where you analyze the results and try to basically detect and identify potentially measurement errors. So if this is ran and it's okay, then you will have what we call the man-machine interface, where the results are basically shown in an operating center every so many seconds. And the results, of course, of the state estimator are used in so many applications, as I said, for protection, operation, controls. So this is overall the framework that we have. And I took this from Monticelli, a fellow Brazilian that basically shows all these fuel steps of the state estimator. And specifically on the this stage here, the state estimation stage, we have several solutions, but they are small changing regarding the models, meaning that they're usually quasi-static models. So they're taking a picture, if you will, of the grid and trying to solve that picture or that frame with regards to a static approach. So while there has been some proposals since the late 70s, early 80s of using dynamic models, as several between them, the Kalman filter family, you have nowadays used by the great majority of utilities quasi-static models. And on them, the weighted least squares solution is probably the most used. And on the weighted least squares solution, basically what you have is a measurement model where Z here represents the variables which are measurements. So like I said, power flow measurements, power injection measurements, and voltage measurements are the most common. And you have a function, h of x, that can be linear or nonlinear, and which relates, if you will, the system states to your measurements. And since the physics show that you have several uncertainties related to the measurements, you will model these uncertainties, and usually they're modeled as a normal distribution with zero mean and a known covariance. And this measurement model, of course, you can transform it into, if you will, a weighted least squares approach by considering that these are basically over-determined. So you will find actually the best solution by finding this, if you will, estimation here, which is the solution of this minimization problem. And the weighted least squares solution, which is really the weighted norm of the residual, is the most used solution. And on that, the weights are usually considered as the invert of the covariance, meaning that if you have a specific meter at hand that has a high precision, you want it to have, of course, a high weight in your solution because the weight will attract the solutions toward it. So this is the main approach that is used, and you have some variations to it, and those are regarding to the objective function. So you have the weighted least absolute value, the weighted least median squares, and you actually have as well, depending on the application, linear solutions where your h of x is actually a linear function relating the system states to your measurements. And more recently, you have as well different time samples of measurements, meaning measurements that are actually sampled in a fasted sampling rate, which allows you to, of course, create so many other applications. These, of course, will change, if you will, your measurement model. And they allow, of course, other, if you will, use of information since they were coming at a much faster rate. But throughout the applications that we found in industry, great majority of them use the weight least squares or these variations regarding the weight least squares. Once you have that objective function and you have some constraints as well in place, the overall solution method is pretty much the same, and you minimize it, and the minimization for it is usually done through the first order optimal condition. So you consider the first order derivative equal to 0, and then you solve, if you will, the linearized version of the residual. And then that solution of the linearized version, you use it towards finding a new estimate, and you do this iterative process until you reach a certain convergence. And the convergence could be several, and one of them is usually the system state, if you will, having a change or being so small towards a pre-established value. And on that, you have this process that is done through the gain matrix that allows you to estimate these values. So this is overall what is in place. And the bad data processing that is in place nowadays is for detection these hypothesis testing solutions. And the most used is the chi-square test, where you have a certain degrees of freedom in a certain, if you will, confidence level. And based on those, you will establish a threshold value, and you will calculate your normalized residual, so the sum of your normalized residual, to this threshold value, and based, of course, on the normal distribution characteristic. And this hypothesis testing would then let you know if you have bad data or not. So that would be data that is incorrect, considering a certain level of confidence regarding the meters that are sending that data. And for identification, what you have in place nowadays is what we call the normalized residual test. So basically, that's when one analyzes the largest residual, and considering as well a certain confidence level, the largest one is the one that has bad data. And as a correction step, usually what the great majority of algorithms do is they throw away that specific measurement that was identified as being bad data or with gross errors, and then they substitute or change the measurement model and run the state estimator again. So going back to that framework, they do that every so often until they have no bad data detected or identified. So that's what's in place nowadays. And what are the problems of those solutions? Well, first, when you're running bad data analytics, or you're running actually the state estimator, you are considering that the measurement model is correct. So you're considering that the parameters of the model and the model is correct. And then you're analyzing, if you will, that the only errors or potential source of errors being them uh, bad data are from the measurements. So that is a strong, if you will, assumption, because one could, if you will, change or the error, if you will, or attack, if you will, the system parameters or the system topology, meaning that the measurement and attack not necessarily needs to be what we call the analog measurements, but they could be the status measurements. So for example, the status of circuit breakers and so on, which would reflect, of course, on the topology of your network. So the assumptions of the state estimator in place, which are currently used towards CPS security, are very strong, but they've been working fine for the conditions that they were supposed to. Of course, when one talks about the increased use of IT and OT in cyber physical security, then you have other challenges at hand. So like I said, you might have an FDI attack, which is the acronym for false data injection, not only on analog measurements, but you might also have those types of attacks on the models itself or the system parameters of the model, or in simultaneous in all of them. So then, of course, the solution in place, which was not designed for that, will suffer. So we initially started the research on such topic by analyzing the constraints of the current solution. And we came about some years ago with some most interesting papers that showed that for the linear case, where the h of x is actually a linear algebraic equation over determined, of course, you would have the specific limitation where the attacks, there were some attacks that were undetected, meaning that when you would have an FDI attack, that was of a representative value, it would not reflect, though, in the hypothesis testing for detection or even for identification. And those attacks were reported in some papers, and we went about studying why was that so. So why did that happen? And why was that so? Why was that if you will, reflection not happening? And of course, initial studies that we did considered the same, if you will, hypothesis that several of the solutions do, which is that you have a certain redundancy level that allows one to consider that due to the central limit theorem, that the residuals actually will have a normal distribution and with mean and known covariance. And still, with all these assumptions in place, meaning that you have a high level of redundancy, we saw that, as reported, that there were some attacks that would not be detected or identified. And our studies showed that the results were mainly because some of these attacks were in the range space that was spanned by the columns of the Jacobian matrix. So that is when you have a geometrical interpretation, if you will, of the residual space, you would see that when you're trying to minimize the weight, the weighted norm of the residual, you're not taking into consideration another part of what we call the error or the composed error, which is in the range space spanned by the Jacobian matrix. So that's, if you will, a component that is not taken into consideration in that minimization problem. And we saw that in certain cases, you might have a small residual, but still have a large component of the error that we called masked, meaning that an attack that would be in that specific range space or be allocated in that range space would go undetected. And that's this paper here that was led by my dad. And he showed mathematically together with us that you could actually estimate that value and then compose the error. So you would compose the error, and then you would, uh, if you will, change the detection and identification test. And that produced excellent results. So we were able to show that for specific attacks, if you were able to estimate that mask component and compose the error, and then apply the chi-square test and the identification test and the correction step, which was then used by estimating what was the error, and then, if you will, changing and not throwing away the measurement, you would obtain great results. However, we saw that a main limitation was based on the assumptions that the detection, identification, and even correction steps, they're all dependent, if you will, of the number of measurements and how best you could model. So they're still model dependent, if you will. And they are, of course, bounded by the impersonation error. So as much as you can model, as much you will have an error. So while initially we obtained very interesting results, we could see that these results were still constrained by the model or by the analytical solutions that we had at hand. And we continued to do research on that. And that research led to other challenges that I wanted to share here with you all today. And another challenge, as I was saying, is that specific attacks, as FDI attacks, could occur as well on static data. So that's when one physically would be able to hack in, if you will, the server that had the files with the system parameters and change them. So as we know, these are not monitored as, if you will, the analog and dynamic data. So these attacks here would be, if you will, very, very, very dangerous, because you would not have, for example, the pre-filtering stage, which would allow us to disconsider measurements that are completely mistaken compared with the previous values, if you will. So we saw that first, the problem at hand was not only FDI attacks on analog or status data, but they could also be on network parameters, which means that when we ran the optimization problem and we're trying to find the best solution, the assumption that the model is correct is strong, because, well, the model might be incorrect. So if the model is incorrect, just like when the measurement is correct, you might find a solution, yes, because the math will solve that problem at hand, but it wouldn't be really related with the physics. So that was an assumption that was, if you will, strong. And as well, we could have what we call topology attacks. So that's when one is changing the status measurements, and the topology processor actually is generating an incorrect bus line diagram. So when you're considering that, you might still find a solution, but again, that solution will be a mathematical solution, but doesn't relate really to the physics, which means, of course, that one could use those and still be undetected. So these presented themselves as additional challenges, and we then started to think on ways how to deal with them, and considering that them all could be simultaneous, meaning that you could have potentially a coordinated attack, a smart attack, as we call them, that would involve all of these potential, if you will, blind spots of the current solution. So one way that we investigated was, as I stated before, to use data-driven models. So use the information that is currently being available through the installation of all these new smart grid technologies. So as smart meters, or as reclosers that you have metering and that can be sent to the operating center. So all these new meters that are out there, but that one doesn't currently use, or not to its full potential, that one does not model. So how can we use that information through data-driven solutions, but in a way that you still consider the physics, you still consider the physics-based models. You want to use that together in an embedded solution. So using them together was our vision. So the first approach to that was to just simply enhance or augment, as you will, the chi-square test by basically including a data-driven model. So if the conditions are the same, meaning that you still consider that you have a normal distribution with zero mean and a known covariance, then that could be applied to any model, if it's data-driven or if it's physics model-based. So what we did as a first if you will, step towards contributing to the solution of this was including in the physics model test or physics model-based test data-driven models, and that was through the augmented chi-square test. So what we initially did towards that was to calculate what we call the Mahalanobis distance, and that is calculated specific Rx calculation and this mu calculation here. So one calculates the mean value and the other one calculates the standard deviation or the covariance, and then you would be able still to calculate, if you will, a residual and apply, if you will, to that residual the chi-square test, augmenting, if you will, the chi-square test. And we were able to obtain through this initial study better results compared to the state estimator itself. When I say here the state estimator itself, I mean the one where we're actually composing the error and not only considering the residual. And we saw in the confusion matrix that we were able to improve much what we have as false positives. So we improved very much there, but we sort of like suffered regarding the false negatives. So when you had an anomaly that was actually not seen. So there was a trade-off between those, but we overall saw results that were satisfying towards the inclusion, or if you will, the use of both data-driven models and physics models together in a way that they would help each other, if you will. And with that, we started then doing other investigations towards using both. And these investigations were specifically to these FDI attacks in measurements, parameters, or topology. And these involved first dimensional reduction. So we started saying that, well, we might have information that is the temporal characterization, which is not implicit in the quasi-static model through the data-driven approach. But when we analyze, of course, the covariance relationships between them, we saw that it was full of zeros as expected. So we could as well, if you will, reduce the dimension, which is, if you will, giving a spatial template, a spatial, if you will, flavor to the temporal characterization of the data-driven solution. And we did that automatically through dimensional reduction. And then we analyze it through PCA, which analyzed the principal component analysis. And towards doing that, we as well applied some studies regarding feature selection. And that meant that, well, our solution so far was pretty binary, meaning that you have a detection or you do not, and it is this fella or is this not. So it's pretty binary. So we wanted to go towards a fuzzification, meaning that we don't want to be binary, but we want to give, you know, a certain probability or certain expectancy that that specific decision was correct. So we studied the Choquet integral. So that's when we fuzzify the results, and then we apply this integral that would give us sort of like an idea of how best or how close or the likely was our solution. And that change from, if you will, this black and white approach to a more, if you will, a possibility approach where you give a possibility of your answer being correct. And that improved, if you will, the overall problem that we were having at hand, which was having all those false negatives. So when we analyzed this combined model, but now with this uh, um, uh, feature selection using the PCA and the Choquet integral, we obtained an overall F1 score much higher than the state estimator, meaning that the accuracy and precision was much higher regarding the physics model solution, which was expected because it's unfair actually with the state estimator because he has no temporal characteristic, right? He just has this spatial characteristic, and he doesn't consider any, if you will, updating of its covariance or its mean or anything. So we expected that, and the results showed that we could get that, and we showed that the costs was actually not that high since these could be implemented rather easily in algorithms where you're basically calculating in a certain window, a certain mean and a certain standard deviation, not needing any additional model, right? So that could be basically augmenting the current solution. So again, it would be an easy and not costly solution that you would include in the framework that already is at hand. But by just using the data that is in place, which currently is not used, I forgot to say, but currently all the data that's coming with a faster sampling rate as PMU days and so on, they're basically not considered. They just will consider the last scan towards the quasi-static model solution. So they're basically disconsidering all the rest. So of course, if you want to use that, one way is through a data-driven solution, where you're going to generate your model through a data-driven approach and then augment, if you will, the chi-square test. Um, uh, as well in our group, we studied another approach towards this problem. And the problem was that while we did consider, if you will, that we had a redundancy that was enough for one to consider the central limit theorem as acceptable, meaning that your residual would have a zero mean and a known covariance in a Gaussian normal distribution. We came to the challenge that that might not be for all areas of the system, meaning that you might have an overall global redundancy level that is above 3, but in certain areas you might have a value that is actually not. So you might have areas in your system that you have a less number of measurements and the redundancy is smaller. And of course, in a logical sense, you would say, well, those areas, of course, are more prone to failure for your detection and identification tests, because of course, your assumption is further away from the truth. That's seen on numerically through several tests, and even analytically through the analysis of the error itself. So that being said, we started investigating how could one improve these solutions through a simple and not costly approach. And one way that we investigated is what we call synthetic measurements. So these are measurements that are not you should not confuse with pseudo measurements. So these are otherwise measurements that are created in the state estimated process. So they're not based on historical data. They're actually created in the state estimator process with the overall idea to increase, if you will, artificially redundancy at certain regions or areas of the system towards improving security, CPS security. So how do you increase redundancy if you don't have historical data, or if you don't have information at all about that specific system? So the way that we went about initially was, again, through using data-driven solutions. So that's where you have, if you will, data nearby, and you use that data nearby in a rational approach towards creating, if you will, new weights nearby that region, and solving with those new weights, if you will, a new state estimation. So it's a two-step approach. You use these new weights based on a data-driven approach to solve the state estimator and create artificially power flow measurements in areas that you don't have. And those power flow measurements, since the weights that you used are not are linear independent, if you will create a linear independent solution compared with the weights that you use on the second step, which are based on a percentage of the magnitude value. Then this additive information is actually information. It's actually information useful. It's not redundant information. So those solutions will create, if you will, additive information in your system that we call synthetic measurements. And those would be then power flow measurements that we would then use as synthetic measurements towards analytics. And this approach was applied for several CPS challenges, including technical loss and non-technical loss diagnosis. And it was published in this work here. And we obtained excellent results. And the process is very simple. So you would have a data-driven approach that uses information from the area at hand. There is an automatic process to determine that area at hand, and that is, of course, then used towards the creation of these synthetic measurements. And these synthetic measurements then would be used towards the weight least squares solution that would then generate, if you will, flow measurements that would then be used in, if you will, the second step, which is this bad data analytics that would analyze then FDI attacks and so on. And we presented the results in this other paper where we actually prove that these would be, if you will, additive information and not redundant. And as well, we show that, well, while you might have all these different types of FDI attacks, like I said, the parameter or the measurement or the topology, how would one go about solving them? Well, you might detect, but then you need a second step that needs to be extended. That is the identification step, which is it, you know, a measurement attack, or is it a parameter attack, or is it a topology attack? So we showed some math on how to go about that, and then some math as well on how to correct those. And the current solution, of course, was through, if you will, the elimination of the measurement. But when you have a parameter attack, you can't do that, so you need to correct it. And what we did was proposed, if you will, in a iterative approach that was better than the current solution that was just basically augmenting the state vector, which would of course require a redundancy level at the area which you didn't have at first place, so which wouldn't work really well. So we proposed that solution, and we were able then not only to detect and identify those different types of attacks, those three, but actually correct them as well, correcting the parameter attack as well as the topology attack and the measurement attack. I'm reaching here the end of my presentation. We as well, more recently considered that the attack on the parameters might be unbalanced. So that means that you would need a new model to consider that, meaning that if one physically would attack the file that had all the parameters of the system and would change that randomly, right, with the intent of actually obtaining the same result, the same measurement, how would you go about correcting them? So we proposed a model that was initially a determined model, and then we proposed an over-determined model that is still in a iterative process, but that would allow, if you will, the correction of the of the attack in the parameter. So this was just recently published, and we compared it with the previous solution that did not, which was the solution that considered the attacks equal in percentage on every parameter. So for example, you pick up or select a parameter in a line and you consider that all of them were attacked by a certain percentage as 30%, 40. Since they're not monitored, you can actually put any value there. And we showed that the current solution sometimes could converge, but it would converge for a wrong value. And while our model did converge for a correct value in a smaller number of iterations. So this is something more recent that we obtained. With that, I think I reached here the end of my presentation. I had some other slides to present, but I guess that it's a lot of information for one talk. I'll stop here and thank again Dr. Gross for inviting me for this presentation. It's a great honor to present to you all some of the current research that we're doing here at the University of Florida. And with that said, I ask you all if you have any questions and give back the word the word for George. Thank you.
So any questions from the participants? Okay.
Yeah, I guess I had a
Go ahead.
question kind of about what your perception is on the trade-off between the benefits of this added data that we have with smart grids and all of the different meters and things that are connected, and the additional points of attack that opens up. Obviously, in your research, you're finding ways to take advantage of that, big data access so that hopefully they don't pose a risk. But do you think that having all of this data creates some amount of risk at the same time?
That's a very good question. Yes, I do believe so. When you have all that amount of data, you have several new challenges that appear, right? Privacy, security, and so on. And that said, I don't believe there is a way back here. So that's here to stay. So my vision is really towards how do you address these challenges. So nowadays you have several cities. I don't know they're in Urbana, Champaign, but here in Florida, several cities do have smart meters already in place, and it depends on the contract that the utility has with the communication company. But usually information is sent every 4 or 5 times a day, and so that's here to stay. So then what do you do with it, right, towards increasing efficiency and security, which is what overall society wants. So I do agree with you. I think there's several additional challenges that appear that were not thought maybe before. I don't believe that there's a way back. So my vision is how to go about finding solutions towards those challenges that are not very costly. And the trade-off is, like you said, you have all that data and one can use it towards, simple things as, I don't know, their energy consumption reduction or even their monitoring of their specific bills, or to more, I don't know, sophisticated solutions as real-time monitoring. So it came to stay, and so there is this trade-off that is privacy, security, and but I guess that if we go about finding solutions that are not very costly, we can address the challenge. I don't know if that answered your question, but yeah.
Yeah, I was just curious on your perspective on that. Thank you.
This is part of your DOE work, Arturo?
No, this is a part of an NSF work.
Okay.
Yeah, this is more research, I guess. Yes.
Well, it's very interesting.